Hello students, I am Shatabdi Acharya from Vedang Institute of Technology. In this video, we will be discussing about firstly the directional nature of bonds. Directional nature of bonds. Basically, the directional nature of ionic bond and covalent bond. So, first of all, let's see, ionic bond is formed by ions, right? Suppose if I am taking NaCl, again NaCl is formed by Na plus and Cl minus. So, after a sodium atom loses one electron to form Na plus is a positively charged sphere. This cation is a positively charged sphere and it has the tendency to attract negative charge from any direction, right? It can attract negative charge from any direction because it is a positively charged sphere. Now, if same is the case for anion, it is a negatively charged sphere. It has the tendency to attract positive charge from any direction. So, basically, therefore, we can say the ionic bonds are non-directional. Okay. Non-directional means they do not have any particular direction of their bond. Okay, you cannot say the bond is directed towards this or something. There is no particular direction for a ionic bond. But in case of covalent bond, what happens? In case of covalent bond, how this bond is formed? By mutual sharing. Okay, suppose this is an atom A, this is an atom B, they have one electron each, they share that electron among themselves and this is the sharing region or the bonding region. So basically this particular the covalent bond has a directional nature, like the bond exists between or in the region of this two atoms. It is directed from one atom to the another. Okay, therefore we can say covalent bond is directional in nature. Covalent bond is directional in nature, whereas ionic bond is non-directional. Okay. This particular thing I missed in the previous videos. So here we got an idea that covalent bond is directional in nature and ionic bond is non-directional in nature. So after this, we will move on to certain bond parameters. Okay. Bond parameters. Bond parameters means what are the factors or what are those parameters which gives us information about a particular type of bond, right? So what basically, like how many bond parameters do we commonly use? The first of all is bond length. Okay. The second is bond angle. Third, bond enthalpy. The fourth is bond order. Okay. So we will be dealing with these four bond parameters in detail in this particular video. So what is bond length? Obviously length means distance. Okay, length is a term used to measure distance. So here bond length means the length of the bond or the distance between two atoms, right? So bond length means, let me erase these. Bond length is distance between the bonded atoms. Now, the measure of bond length is different for different kinds of bond. If I consider ionic bond, the bond is formed by a positive and a negative ion. So what happens? An atom loses electron, it forms a negative ion, sorry, a positive ion. Suppose the radius of that positive ion is Ra plus. Okay, and another nonmetal, it gains electron to form an anion. Suppose its radius is Rb negative. So what will be the total bond length of that? The distance from Ra, the radius of Ra plus Rb, because they will be basically present like this. If this is the radius of A and this is the radius of, this is the radius of B. So the sum of the distances of the radius of both the ions give us the entire bond length. So here the bond length can be represented as Ra plus Rb minus. This is the bond length for ionic bond. Now if I compare covalent bond, how a covalent bond is formed? See, we will understand covalent bond in little detail. Imagine a situation, two atoms are coming from a distance. Okay, two atoms are coming from a distance to be covalently bonded. Now what happens? There is attractive as well as repulsive forces operating between those two atoms. What are those attractive and repulsive forces? Suppose this is the valence shell and here the positive nucleus is present in one particular atom. This is another atom. Here the nucleus is present, it is positively charged. There will be certain attractive and repulsive forces, right? As I said earlier. Now the attractive forces will be between positive and negative charges. Okay, suppose here one electron is there and here another electron is there. Now let us see in detail what are the attractive and repulsive forces here operating here. Okay, so in the first case, electrons and nucleus of one atom will undergo an attractive force. In the second case, electron and nucleus of the other atom will undergo an attractive force. Now there will be repulsive force also. So what will be that repulsive force? Now nucleus of one and the nucleus of the other, there will be repulsive force. Electron of one and electron of the other, negative negative they will repel, positive positive they will repel. So the net bond length will be when the atom overcomes these attractive and repulsive forces, right? So basically what happens when the atoms are at a distance where the positive attractive and repulsive forces balance each other, then we say a covalent bond is formed. If we try to understand this graphically, okay, when an atom forms a bond, it undergoes stability, it becomes stable, therefore its energy is lower, right? So if I try to represent it graphically, what will happen? Suppose this is the distance, this is the energy. Okay. Imagine a situation when the atoms were at a distance. They were at a distance, then they came a bit closer, again in a situation where they came very much closer, like they penetrated each other, right? Three situations. Here what will happen? When the atoms were at farther distance, they were not stable, they were at a higher energy. Gradually when they came closer, the attractive forces dominated and the energy became less. Gradually when they penetrated into each other, the repulsive forces between the nuclei of both the atoms started dominating. As a result of what happened, the repulsive forces came into being and the energy increased gradually. So if you observe the graph, they at a particular distance, they will have a lowest energy or stable structure, and that distance is basically called as bond length. Okay, So bond length is that distance where the energy is minimum. Energy minimum, stability maximum. So in these situations, this was atom A, atom B, they were at a farther distance, they were having high energy. When they gradually came closer to each other, the energy tried to decrease and it attained a minima where the atoms were highly stable or in the minimum energy state, which is called as the bond length. Now when they further penetrated into each other, their nuclei came closer to each other, then they started repelling. Electrons also came closer to each other, so there is a repulsion between the nuclei and the electrons. As a result, the energy rose to a higher level and they became unstable. Then this particular distance where the atoms are stable, balancing all the attractive and repulsive forces, it is known as the bond length. So in case of covalent bond length can be considered as radius of A plus radius of the second atom B, Ra plus Rb. Okay, this is the case of covalent bond, the bond length of covalent bond. Now what happens? We understood a situation where there is not only always a single bond that is formed, there are also chances of double bond and triple bond. When two electron pairs are shared, okay, then it forms a single bond. When 4 electrons are shared, they form a double bond. When 6 electrons, like 3 of one atom and 3 of the other atom, they are shared, they form a triple bond. So gradually when the number of bond is increasing, their distance will become closer to the atom, because as the negative charges is increasing, the force of attraction will also increase and the atoms will come closer to each other. Therefore, with increase in the number of bonds, the bond length decreases. Okay, A, single bond, the bond length is greater. They start forming double bond, bond length decreases. With triple bond, the bond length further decreases. Okay, so with increase in the number of bond or multiplicity of the bond length decreases. Now we'll move on to the next parameter, which is bond angle. So how we know a bond is formed? A bond is formed by the overlapping of orbitals, right? A bond is formed by overlapping of orbitals. Now when the orbitals overlap, they will do so in certain angles, right? So the angle in which the orbitals overlap with the central metal atom is called as the bond angle, or the bond angle is defined as the angle between the orbitals of the bonded atom. Excuse me. Bonded atom. Okay, so we will be dealing with bond angle in depth. We have further theories about that. We will be dealing with bond angle and like proper discussion will be having of bond angle. But as of now, let us understand, in case of methane, the structure, bond angle is very much related to structure, okay, structure of the molecules basically. So in case of methane, or in case of we have ammonia, then again we have water, okay. Lastly we have PF3. Okay, so in case of methane, the bond angle comes out to be, it is experimentally determined, and bond angle is usually represented as degree, minutes and seconds. Okay, So in case of methane, the bond angle is 109 degree 28 minutes. In case of ammonia, it is 107 degrees. In case of water, it is 104 degrees 5 minutes. In case of BF3, it is 120 degrees. And these all bond angles are experimentally determined. Okay. So next we will move on to the next parameter, which is bond enthalpy. Bond enthalpy is the amount of energy required to break a bond. Okay, amount of energy required to break a bond in its gaseous state. This is very important, in its gaseous state. Okay, the amount of energy required to break a bond in its gaseous state. Now understand a situation. Suppose I am saying methane. So here carbon forms 4 similar kind of bonds with hydrogen, right? So equal amount of energy must be required to break these 4 bonds, right? So we must be requiring a particular amount of energy to break all these 4 bonds, because all the bonds are equivalent. But exactly what happens if we break this bond one by one, like one after the other, then the amount of energy required to remove the first hydrogen is not same as that required to remove the second hydrogen. Let us see what I mean is, suppose CH4 forms CH3 plus H. In the second case, it forms CH2 plus another H. In case of it forms CH plus another H and C plus another H. So we need to break 4 bonds with hydrogen, right? But in that case, the bond energy in all the cases should be similar, or it should have similar amount, it should be requiring similar amount of energy to break all these 4 bonds. But no, because what happens when the first bond breaks, the electronic situation around the atom changes. Similarly, when the second bond breaks, the situation again changes. Therefore, the bond energy actually required to break these bonds is different in all the 4 cases. So what we take the exact bond enthalpy is the average value. It is the average value of all these. Suppose in the first case I will be requiring X amount, next Y, Z, and this is suppose A. Then the average of these will be called as the bond enthalpy of CH4. Okay. So now we understood what bond enthalpy is. Next we will go to bond order. Bond order basically means the number of bonds between 2 atoms. Okay. Bond order means nothing, it is very simple. The number of bonds between 2 atoms. Okay. So if 2 atoms form a single bond, their bond order is 1. If they form a double bond, their bond order is 2. Okay. 3, 4 similarly. And also bond order can also be fractional. Okay, they can be they can have fractional or decimal values. We will understand to calculate bond angle when we read a theory called molecular orbital theory. We have that theory in this chapter only. We will be dealing with it in the upcoming videos. Okay. So basically understand, here in this video what the bond parameters we are studying is just a preliminary idea, because in depth we will be dealing with all these bond parameters separately in the upcoming theories. Okay. So this is bond order basically, which means the number of bonds between 2 atoms. Now we will understand the relation between bond length, bond order and bond enthalpy. Okay. If bond length increases, that means distance between bond increases, what will happen? It will be easier for the bond to break. That means bond enthalpy will be high, or sorry, bond enthalpy will be low. That means bond length is inversely proportional to bond enthalpy. Now, if the number of if bond order increases, then bond length will decrease, right? So bond order is inversely proportional to bond length, and if bond length increases, bond energy or bond enthalpy, okay, sorry, it is directly proportional. So if bond energy is, bond enthalpy is more, like bond length is more, then bond enthalpy will be more, but if bond order is more, then bond length will be less. It is inversely proportional. Now last thing we'll be dealing up here is resonance. Okay. So basically resonance means, to understand resonance we will take an example of ozone, O3. How was the structure of ozone? This. Okay. Now I can also represent it, the structure, like this also. So this is structure 1, this is structure 2. Now this, both the structures might be looking different to you, because what happened, suppose I am numbering this carbon 1, 2, 3. In the first case the double bond was between 1 and 2, in the second case the double bond is between 2 and 3, right? So there are two different ways to remember, like to represent ozone, but what is the correct structure of ozone? So experimentally it was determined. Now this is the single bond, this is a double bond. So these bonds should have a bond length of the double bond which should be shorter than the single bond. Same is the case here also. But experimentally it was found that all the two bonds in ozone are of equivalent bond length. This concept led us to resonance. What it means, the structure can be represented as like this. That means this pi bond is uniformly spread out between both the atoms. This is basically called resonance, that is delocalization of pi electrons. It is called as delocalization of pi electrons. That means the pi bonds are not localized in between two atoms, rather they are spread out in the entire structure, okay? And these structures are called as the contributing or canonical structures. These are called as the contributing and canonical structures, and the resulting or the final structure is called the resonance hybrid. Resonance hybrid, and resonance hybrid is the lowest energy structure. These are the contributing structures or the canonical structures are the structures of comparatively higher energies, okay? And it does not mean that this structure is like keeping on oscillating between these two structures. No, there are different, they are just different ways of representing this structure. But here the actual structure is like this. The resonance hybrid is the actual structure, and these are basically the contributing structures that like add up to this structure, okay? This does not mean this structure is particularly oscillating between, like at one time it will be present like this and the other time it will be present like this. No, these are basically, these two structures add up to the final structure, which is the resonance hybrid, okay? So I guess you understood what bond parameters are and what resonance is. So that's it for this video. In the upcoming videos we'll continue further. Thank you.